git commit, git push about 5 minutes ago slides.
Okay.
So you need to know about templates and whatnot for the rest of the course. And I was actually pretty surprised that, what is it, about 10 of you put your hands up earlier, when I think Maro asked who knew what. So you don't know a lot about templates, which is, on the one hand, it's good because this material will be new to you, but on the other hand, it's kind of bad because once you start doing templates, things escalate rapidly in terms of the kind of complexity and nonsense of what you see on the screen. So the reason we like templates is because they let us do generic programming. What's generic programming? It's basically writing something once and then using it lots of times for different things. Wikipedia has its own description of generic programming. What we really hope to get from it is code reuse. What you want to do is you want to write an algorithm once and then be able to apply that algorithm to lots of different things, or at least the same. Every time you write the same structure in your code multiple times, you think, well, I could just do the same as that with this. Then you think, well, I could template it on some type, and I could make that happen. The STL was mentioned earlier. We've seen standard swap on screen. We've seen standard unique pointer. We've seen, sorry, that's the standard library, I should say. The standard library has the STL, which is the container library. Actually, it's in the standard namespace, but when it's got vectors and decks and queues, and if you don't appreciate, if you haven't used them, then you can't appreciate. But if you don't appreciate how kind of awesome they are in the way they completely abstract the algorithm from the data. When you do a sort or a find or something, you can do a sort or a find on a list or a vector or a queue or whatever it is, and the objects you store in those things are completely separate from the algorithm. And this is where generic programming is trying to come in and help us. To let us write the algorithm, something like the stencil operator that Maro showed on his first set of slides. It might be a float, it might be a double, it might be a complex type, it might be some user-defined type. If you could write that stencil once and then have all of your stuff just work with multiple implementations of it, it would be great. So we're looking at code reuse, abstractions of algorithm data, API. Once you start creating a library where you define an API, people use it and they stick to it. And if you look at the STL again, people use the same push back, push front, pop. They appear in the stacks, in the vectors, in the queues. They appear over and over and over again, and you just keep reusing them. And you can go beyond that into more advanced sort of programming where you start, instead of just specializing the algorithm, you might even start specializing some of the operators which happen. So you've seen in C rather that you can overload operators. You can redefine the plus sign to do something different when you give it 2 integers or when you give it 2 strings, for example. You can add 2 strings together. It's a fundamentally different operation, adding 2 numbers together. And you can define your own types and customize the operators. And then you can start writing algorithms where you can even pass in what operator to use or sub-algorithm to. So you can say find this, that, and the other in this list of numbers, and you can do customized operations by passing in functions rather than just data. So just a reminder, what do we mean of functions and classes? Well, a function exists. You write the code A plus B, and you call it add. And the compiler compiles that, and it produces a block of assembler, which it sits there in your code. It exists. It's there. When you write a class, you say, I've got a class, and I'm going to put some things in it. It's got some member data. It's got some functions in it. Those get created by the compiler at compile time, and they sit there, and they're kind of in your code. You may not use them, but they're there. And here's the magical slide that Maro was looking for, is what's the difference in a class and a struct? Maro knows. I mean, the only real difference is that the struct is what it was called when C was around. It was called a struct, and it was a thing where you could put lots of objects in it, and you wrapped it up into a structure, and then instead of passing all the individual bits, you could just pass one structure. By default, everything in a struct is public, so all of the objects in here are visible throughout the code, whereas in a class, by default, things are private, and you have to specify that this is going to be public or this is protected, depending on how you inherit. Inheritance. If you're not familiar with, everybody knows about inheritance in programming, yeah? Is anybody like inheritance? No. Okay, good. That's fine. So, was there anything more you would like to say about structs and classes before I move on? Okay, I'll just move on. So it's basically, wherever you see struct, you can think class, or wherever you see class, you can think struct. The only difference is the visibility of the internals, and it really doesn't make any difference. There's no magic anywhere else in there. And so you can instantiate classes, and here, functions, member functions of those classes and data, they exist in the code or in the data segment. But templates aren't the same. Templates don't exist until you instantiate them properly, because if I say foo of t, and I say, I'm going to allow this function to exist for any type of t. This is the basic, your first basic template definition. Here's a function, and I might pass it, I might specialize it for an int or a char or a double or even a string. None of those things actually exist until you instantiate them down here. If I delete, I'll show you what I mean. In fact, before I flip screen, if I try to take the address of a function, when you compile some code, you get a function, and that function exists somewhere in the linkable. This is what the linker does: is it links all those things into the final executable. But that function exists, and you can take the address of it. You can't take the address of just this foo, because this foo doesn't exist unless you specify that it's a foo specialized on an int. And I'll show you what I mean by clicking on this link. He says, hopefully. So this takes you into the Compiler Explorer, which Fawzi introduced to us. And Compiler Explorer, I'm going to use it a bit throughout this presentation because it's kind of awesome. And is this too small or too big or anything? Shall I up the font size one? So here you can see I've got a function add, and the compiler has generated add, and it takes 2 ints as parameters, and this is the code. And when I move my mouse over it, you can see the highlighting do its thing. And down the bottom, you can see it's also created a foo of a string and a foo of a double and a foo of a char, because I put those in the code down here. But if I delete all of those and I just comment them out, then the compiler now says, okay, fine. Now, it actually leaves the add in there, because I don't have to actually call that function add for it to exist. The compiler has compiled this, and it says, I know what X and I know what Y is. Now, when you actually build your executable, the linker might say, you never called add, and it can just delete that. But it does exist in the sense that the compiler knows how to make the code for it, so it's there. So that's really the difference between the instantiation of a template and just the kind of presence of a function. It's worth pointing out that what we did before is we said you can have foo with an int or a char or a float or whatever. You can do this with functions. You can just say, here's a function which takes an int. Here's a function which takes a float. Here's a function which takes an int and a float thing. And these are all function one. And you can define as many functions with the same name as you like. And it's just called overloading. There is no magic there. The compiler already knows how to handle this. And the only catch is you can't go around saying this is a function which takes an int and returns an int, and this is the same function which takes an int and returns a void. Because now the compiler is going to say, oh, which one do you want me to use? You're passing an int into it. Do I return the void or I return the int? And you might say, well, what you could do is you could look at what you're assigning the result of that function to, and then deduce, sort of guess which function to use based on that return. But actually, things fall apart because the number 3, it could be an int, it could be a float, it could be a double. Things can be automatically changed from one type to another in C++. And so it's just too hard for the compiler to handle it. So one function with a given name and a given set of parameters is all you're allowed. So you can't just go around doing multiple of them. There is an exception here, which is that if you throw in a const here, that makes this function a different function, because it's now got a different signature. It's no longer exactly the same. So you can, and obviously you can't put a const on just a bare function. These are just bare functions. They exist in the global namespace. This is a member function of a thing. And so this const means that this thing isn't being modified. You can't put a const here because it doesn't mean anything. There's nothing to be consted. You're not changing it. So this changes the signature, so you can do that, which is how, for example, you'll see in lots of code, there's 2 copies of lots of things where one of them is just bare and one returns a const, and that allows the compiler to pick the const one whenever the cost, and that allows optimizations. That's just a side note. So going back to the idea that functions can have the same name but have different types in the parameters. So here's our foo again, And when I actually call foo with int, and I say, I would like you to instantiate the int version of foo, and I'm passing an int into it, it will call that function and pass an int to it, and everything's fine. I've explicitly said, I want an int, everybody's happy. The second one, I've explicitly said, I want a char, and everybody's happy. And those of you who were born in the 1970s or whatever will know that the ASCII code for the symbol A is number 65. And so it turns out that char, which is convertible to a char, will print out an A here. So if I print these out, then the first one prints out the number 65 and it says I. There's a nifty little utility built into C++ where you can say type ID of name. And I've stuck this onto lots of the slides just so you can see what's being generated at the bottom here. So 65 integer, A, char. Here, I haven't said what I want. The compiler says, this is a, 3.14, it's a double precision. It could choose float, but if I would have to put an F at the end of that. It's what's known as a literal. In this case, if you don't specify, but you use a decimal point, it assumes it's a double. So it says, well, this foo, and it's using a double here. I didn't say instantiate foo with double in, but it can deduce the term, or rather the template type here. So this is a type of argument-dependent lookup. It used the argument to look up now there's more to ADL, which I'll come to in a little bit. But this is your sort of level 1 ADL, where it just says, you've passed a double here, so I better pick the double version of that. And if I explicitly say double, then it also uses the double. And likewise, this is an int by default, 3 on its own with no decimal point. The compiler says you've put an int in, but an int is allowed to be converted transparently to a double, and so it chooses the double one, everybody's happy. Similarly with the string one here. I didn't say I want standard string, but because I've explicitly said that this is a string and not a char pointer or a char or whatever, then it will choose the string version. And this is just argument deduction. And this is how the compiler effectively decides which version of the function to call. And this is no different, effectively, from really what we did, that's the wrong way, beg your pardon. This is no different from just regular function overloading. When you template a function, all you're doing is saving yourself writing it out 27 times. There's no real magic going on. The magic really comes in when you start templating classes, which I'll come to in a minute. I didn't skip a slide then, did I? Yeah, that's the right one. And then but the order does matter. So if you have multiple template parameters in a function, so in this case t and u, you have to make sure that if you say, I want string double, and then you put string and double in here, that's okay. You haven't surprised it, and nobody's surprised by this. If I say just string, then it assumes the first one is the string, and so if I put a string in, everybody's happy. If I say just double, and I put a second one as double here, it says, hold on a minute. You've said double, and it can't deduce the string for t because you've put the first one and it just assumes the first one is t, and it can deduce u, but it can't deduce t. So if you try this line here, it'll say can't convert hello, and notice how the type of hello is const char 6. It's not string, it's not char pointer, it's const char 6. It's a very specific type. It's saying 6 characters, including the null termination, whatever. Yeah, 5 letters in hello, just checking. 5 letters plus a null termination. It's a const char 6. You can't change it, it's const, it's 6 characters including the space, and it can't convert it to double. Fine. And so you can't just go around rearranging things arbitrarily, but do watch out for when functions which have automatic conversions, like you can convert char to string in certain places, and you can convert int to double, and you can convert double to int if you put a cast in the right place. Always watch out when using templates for these automatic conversions, because they can really bite you in a very painful way, because things which you didn't think were the correct match for something, it turns out they match because somebody added an overload somewhere, and we'll come to that in a bit. Yeah, please. So I should have said, do ask questions, and especially as I know that a lot of you, for example, English might not be your native tongue, and I do tend to speak a bit fast and get, quite excitable, so, interrupt.
Okay, so there's something like explicit, where you can tell a function, tell a function in your class, I explicitly want you not to convert the input? Is there not something like that
Oh,
for,
yes,
for
okay.
templates?
Yeah, when you define your own struct or class, and you say, my struct or class is a thing, and there are certain times when I want a thing to be converted to another thing, I can make that conversion operator explicit, and I can add an explicit keyword to it. And what that does is it tells the compiler, don't automatically replace 3.14, or rather, don't automatically, in this case here, don't automatically convert 3 into a double, unless the person specifically casts it into one of those and asks for it, and that's the explicit keyword. But I don't cover that in these slides, so it's very good that you asked, so points. And I don't remember what slide I was on. Was it that one? It was this one, wasn't it? Yeah, so if you put 2 template parameters, then you have to supply 2 template parameters to the function that you're overloading, or whatever it is that you're overloading. In this case, if I say to and from convert number 1, and I'm saying from is here, then the parameter which is passed in here can be guessed by here. I put a D here, which is double, and I say, and so it can guess that D is a double. Everybody's happy. But I have to explicitly state the first one as int. I want to convert to an int from a double. In this case, the order is okay. The fact that I've skipped, or rather, I've put the first one in and I'm deducing the second one, that's fine. In this case, I deduce that D again is a double, and the first one I've explicitly stated 2 is a char. And the third one here, this is a more complicated one. If you've ever seen pointers to functions in the old C notation, they're horrific and they look like this. But what this says is that I've got a function which takes a float as a parameter, and it returns an int, and this is a pointer to a function effectively. And again, it can tell me that the function takes a float as parameter. I beg your pardon, I've done this wrong. The return type is 2, so I'm converting to an int, and I'm converting from a float, which is the parameter that's going in here. Because what it's doing is I'm not explaining this very well, it's mapping this declaration here. This is the function, and it's saying, what type of function is this? And it takes a float and returns an int, and it deduces that from this. I haven't explicitly stated anything in the sort of template squiggly brackets, which I didn't mention the squiggly brackets, but this is how you tell what the templates are. And so then you can call that function there, and it returns, in this case, you've got int double, char double, int float, and these are the ones that come out of the output of here. If you flip these parameters round and you say from and to, but you leave everything else basically the same here, then this changes, because now you've said that the from here is a double, to is an int, first, second, and this int better match this int here. Likewise, this char better match this char here. And we've done the same. We said to and from, mapped it in, and here it's the other way around, because that should say int, to is char. I've copied and pasted from there, and I've put a char, and that should say int, because that's a return type int, and that's a float. Apologies for that. There are more mistakes on these slides. Points to everybody who finds them. That one was unintentional. The rest are all deliberate, honestly. Anyway, so basically, in order to deduce the types that go into one of these things, there has to be something in the code. If you leave out some of these parameters, the compilers are like, I don't know what you want. You know, I can't guess. If you put stuff in there, if you annotate your functions, if you write the code correctly, the compiler can guess. If you don't, it can't. So when I was talking about automatic type conversion, so when you automatically convert ints to doubles, that kind of thing. This is a little bit more complicated here, because here I've got a thing, and it has an automatic conversion to a bool. And let's suppose we initialize the thing with some value, which we'll say is 1 or 2 or 3. I'm going to initialize a thing with the value 0.05 here. And then I'm going to say print thing. And print thing takes a templated type T. It says whatever the type T I'm given, I will then print it out here. And then I'll print out the value of that T. And it's important that this sum value here matches this sum value here. You can't, if I were to pass in a thing here which didn't have some value defined, then this would be a compilation error because t some value, it wouldn't exist. So you can't do that. When you run this code, without looking at the answer, can anybody see what's going to be generated here? I've got two overloads. This slide actually probably should have come after the other one because we haven't talked about extra overloads. But here we've got a print thing function, which is templated on t, and it takes a t. And we've got a print thing function, which isn't templated on anything, it just takes a Boolean. So now the compiler has a choice of which thing, when I call print thing of t1, which one it should print out. Well, clearly, if I go print thing of t1 with a Boolean, it doesn't work. You can't print a Boolean of a t1. But if I print thing of a t up here, where I've got t can be anything, then this overload t matches, and it prints out t, and it prints out the value of t as 0.05. But interestingly, if I print thing and I cast it explicitly to a bool here, I print thing t1 and I cast it to a bool, I've supplied this operator bool up here. And this is something you'll see a lot in C++, where people overload the operators. And you can overload things like the angle bracket stream operator so that when you print out an object, it does something nice on the screen. You can overload the plus operator and the minus operator and the multiply operator. You can overload not just functions, but operators. And here, we're overloading what's known as the casting operator. If I say, I'd like to convert this thing into a Boolean, this has got a little nifty function built into it that says, well, okay, if it's bigger than 0.1, then we'll return true, and if it's less than 0.1, we'll return false. So when we say print thing Boolean of t1, it uses this overload here, and it says, we're asking for a Boolean. I know how to print thing of a Boolean, so it prints out overload b, false, and false because it's less than 0.1 because I gave it a value of 0.05. So this is your first kind of example of how two functions with the same name can be selected between. And this is a broader category of what choice to make. Let me just step back a second. When constructing an object here and printing it out, in this case, I've provided a stream operator directly for a thing here. This is a stream operator which says, when given cout, we haven't introduced cout. Has everybody come across cout before? When you print something to the standard terminal, you use cout in C++. Print out this, and then return that so that it can be chained in one of these sequences. It's interesting that this call to cout is translated into this function, which matches this function, and so it's called up here. ADL effectively is using the arguments, which in this case, T1 is an argument in here, and matching it to this one up here. We use const in general because when you're just printing something out, you don't want to change it, you don't want to have side effects on the code. You can do something interesting, which is that here, I declared this as a friend, which means that when you call this function here, this thing it has a member function in here, which is the operator, and cout finds that member function and is able to use it to stream its thing out. I can move that function out of the struct so that now it looks basically the same, but it's no longer a member of this class. I can't use the friend keyword anymore, but something interesting happens, which is that if you change this struct here from a thing, this works fine, because everything in thing is private. Everything in thing is public. But if I change the keyword from struct to class, this will no longer compile, because this operator here can't see inside thing. It's not a friend of the class, and so this value here, t, some value, is not visible. And this goes back to what we mentioned about the difference between a struct and I thought I had a link on here because I was going to show it, but it doesn't matter. It's an interesting side effect of the difference between using operators which are part of a class and operators which are not part of a class. And it's a side note to this whole ADL type lookup. This one takes it one level higher because we have a namespace here. If you declare a namespace, everybody's familiar with namespaces. Not familiar with namespaces. Anybody shaking their head? You can declare a namespace. It's basically a scope block. We're going to call this 1, we're going to call this 2. You've got a thing inside this namespace, and it's got some value, and it's got a bool operator so that you can convert it to a type, convert it effectively from a float into a value, true or false. And if we say, I want a thing 1 from namespace 1, and I'm going to give it 0.05, and I want a thing 1 from namespace 2, and I give it 0.07. These are basically exactly the same bits of code here and here. There's no difference there. And then I've got an overload here, which says, print this thing, and it says, I'm in namespace 1, print the overload. And this one is exactly the same, but with a 2. When you print thing 1, it says the function print thing doesn't exist in the global namespace. There's no print thing here. This is all inside namespace 1. But because T1 is inside namespace thing 1, it looks in namespace 1, and it says, is there a print thing function there? And it finds a print thing here, which matches this T. So the template is specified here. You can do it all on one line. You don't have to do it on multiple lines. I'm trying to save space on the slides, so I just did it here. So this T1, when you print 1, it comes out with 1 overload. And when you print thing T2, it looks in namespace T2, and it comes out as this one over here, 2 overload. Now, this sort of thing happens when you define your custom type. I've got my custom matrix type, my custom vector type, and then I want to apply some function like sort my vector elements or something into order, or sort my matrices into the biggest and the smallest. And things like the standard library have got sort functions, and they call operators which expect to find a plus or a minus or a greater than or a less than operator, and they don't know where to find these kind of things. And so this ADL kicks in because when you define your structs and you define operators in different namespaces, so if you have my library namespace and then you have some structs in it and then you apply a standard library algorithm to those things, how does it find your functions? And it's doing this kind of thing in the background. We've seen how to template functions. Templating classes is a kind of step up. Classes, because classes have got data members in them, they can have more complicated data members, and you can also have types. And I'm going to come back to the using keyword in a little bit. I've got some slides on that in a little while. Suffice to say that when you say using type equals t, what you're creating is just a reference to another type. It's called an alias. And so inside classes, you can specify, you can template not just simple variables, but you can template functions within classes, types within classes, data members within classes. Things start to become interesting because, and not to be confused, you can also return the return types, not only the parameters, but the return types of functions within that class can be templated. Things start to get very interesting and very complicated. You can do all of these things here inside the class. And you can specialize so that certain operations will only apply to certain kind of instances of that class. So the classic case here, we've got a simple one. What we'll do is we're going to say we're going to have an x, and it's going to be templated on 2 parameters, t and u. And we don't know what t and u are yet, but what we're going to say is that if the second one, u, is an int, then we'd like to do something special. So we would put some special code in these brackets. This might have some default code that we do, some things. We'll just leave it empty for the time being. So this one, if the second parameter is an int, we want to do something interesting. In this one, if the first parameter is a float, we want to do something interesting. And these are called specializations. We have the primary template, and then specialization 1, specialization 2. And so if we call x char double, it says char double, char double, char double. Okay, the only one that really fits is this one, so it uses the number 1. If we say char int, it says char int, that fits. char int, that fits, but it's better, and float, no, that doesn't fit. This one is picked because more of the template parameters match. So it's a better fit, it's more specialized. So in this case, number 2 is chosen. In this case, by the same reasoning, float double, float anything is better than anything, and it's definitely better than anything int. So in this case, number 3 is chosen for float. When we say float int, it says yes matches, yes matches, yes matches, and the error message the compiler gives you is ambiguous partial specializations. It's saying, I just don't know which one you want, so you're going to have to be explicit. And the way you fix that is by saying, okay, here's a new one we're going to add with float int, and now it chooses 4. The first 3 are unchanged. Now we've added a 4th one, and this is referred to as a full specialization because we've effectively specified this one, this one, this one, and now you see the empty template. What do you call these kind of brackets? Is there a word for them? Angle brackets, thank you. Angle, I should know that. So the empty angle brackets effectively signify this is a full specialization, meaning the templates that are sort of free are now down to 0. But you have to leave this template empty bracket in to tell the compiler this is what I'm doing. Otherwise, this would just look like some weird construction that the compiler wouldn't necessarily pass properly. So full specialization where 2 are specified is better than 1 specializing, which is better than 0, so it picks that one. Everybody's happy. This is Mauro's fault, this slide, because it's kind of awkward what's going on here. When you create your template type here, primary, you can specialize not just on T or U, you can specialize on something which is even more complex than the original. So, for example, here we're saying whatever W is, if the second parameter is another X, X being this thing itself. So it's kind of specializing on itself, but it doesn't matter. What matters is that it's saying if I see something here and the second parameter is an X, then use this specialization, and if this function is just a function which takes an X with 2 T's. So what's going on here? So if I try to instantiate an X, and I give the first parameter as an int, that's fine. I'm allowed to put anything as an int here. And the second one is another X, so I'm templating an object on itself, effectively, which it doesn't matter what that means at this stage. It's just pattern matching. It's what the compiler's doing in its head, if you like, when it's thinking about stuff. Here's an X, and it takes int as the first parameter. The second parameter is also an X of an int and a float. Well, that actually matches this primary specialization. T could be anything, and U can be anything, and so it matches. That's fine. So, in fact, specialization I beg your pardon. It matches the primary one, but if you look at the second one, W can be basically anything, and T and U, as long as they're in here and there's an X of a T and U, well, this is an X, and this T and U are int and float. It doesn't matter if this int here, T, happens to be the same as W. The compiler doesn't mind if T and W are the same, because that's allowed. So specialization 1 here actually matches, X of int and float matches this one here. So the compiler will pick that to instantiate, assuming that nothing else matches it. There may be a whole list of other specializations. Likewise, this one also matches. You can have an X templated on an int, which is second template parameter is an X templated on a char with another template inside it. So it's like having a vector storing a vector storing a vector, if you're familiar with vectors in the STL. And so this matches here as well, and it's fine. And this pattern matching can carry on ad infinitum inside the compiler's memory. It can just keep matching things. And it's basically how it chooses these is it just keeps looking at the parameters and saying, do they fit, do they fit? Now, X of double double of C, it says that doesn't fit this one, but it does fit this one, so it matches the primary. And then if you try and print these functions out here, so foo of C, which is an X of 2 parameters which are the same, notice how this parameter has been reduced from 2 down to 1, and we've got 1 here. this is okay. You can always go down in the number of template parameters, providing the number in the original. Sorry, I beg your pardon, this is not specialization, this is a function. I'm confusing myself with the slide. So foo of C, it says this is an x of a double-double, which is an x of a t of t. It matches that and it prints out. Foo of B, which is this, it says, I don't know how to do that one. So the compiler gives you an error there, and it says, candidate template ignored. It's basically saying, when it tries to do foo of B, it says there's a T and a U here, and they don't match a T and a T here. And it says char of int void doesn't match T of T, because this effectively, it just doesn't fit. The pattern matching algorithm inside the compiler has failed, and it doesn't work. We can add, effectively this part's the same, we can add another instantiation of an x of a t and a u here, and now when we print foo of b, then this actually works. Even though b is an x of an x of an x, it only needs to go one recursion deep to see that there's a t and a u. In this case, u is all of that in there, and that matches. So I'll probably save it for a slide in a moment, but there's an interesting kind of side effect of this, which is that if you have, well, no, I'll save it for a minute, because I've got a slide on templates in a moment. So that previous slide, when you see templating X on itself, it's kind of weird. And there's something very interesting that you can do with C++. And I don't know if you can do it with other templatey languages like D and other things and stuff like that. But let's suppose you have a class or a struct. Doesn't really matter for this. Remember, structs and class are the same. So you have a class and you say, I've got a base controller. And this is something which is taken directly out of my own code. So I use this all the time. And you template it on some thing. And I apologize in advance for passing in a variadic, which we haven't come to yet. Just to assume this is a list of parameters at the moment, and this is just the list of parameters being passed on to the next function. I'll come back to that. You have a class, and you want to initialize it. And if you're familiar with inheritance and polymorphism, you probably remember you can have something like a shape. You can have base class shape. And then I can have a circle, which is a type of shape, but it specializes something, and a square, which is a type of shape, but it specializes, or a blob. And you might have a function like, how many corners does it have? And you put in the base class, how many corners? And a circle returns none, and a square returns 4, and a blob returns, whatever you decide a blob might have. And this is how polymorphism works. You have a base class with an interface, and then you have instantiations of it which supply bits of that interface with different answers. How many edges have you got? How many corners have you got? Can you be filled in? Are you complete or are you open? Are you closed or open? Are you concave? Are you convex? Things like that. And so shape defines an API, and then those other classes fill them in. And the way it's normally done with inheritance in what we would call runtime inheritance or dynamic inheritance is that when you create a circle or a square or a blob, you specifically create one of those, and it stores a little pointer. And that pointer inside it has a pointer to a lookup table. And so when you call a function, which is one of the virtual functions on it, it looks up in that table to see which of the actual classes it belongs to, and it looks them up. And it's incredibly useful. And it used to be used an awful lot in C++ and other object-oriented programs because you can do so much with it. You can have a list of things, and you just don't know what those things are, but you know that they adhere to a particular interface, and then you can look up different things on them. You can have candidates at the conference. They've all been to a certain school. They've all done to a certain thing, and you can replace different types of object in your lists with slightly different constructions. And the only downside is that it requires this extra lookup of these things at runtime, which it can be a performance overhead. It usually isn't a big one. But this is an interesting thing here we've got, because you can create an interface using a base class, and it's got, for example, an initialization function here. And here I'm going to take a controller, and I'm going to derive my controller from the base controller templated on myself, which is what we saw a moment ago. You've got X templated on effectively kind of X. This controller is templated on a controller here, and no, this controller base is templated on controller, and so I've got a function now which is the initialize. Now when you call initialize on the object, it actually casts the pointer to this, to the derived type, which is the template parameter here, and then calls the function on that. So this will actually route itself directly through to that. Now, what you've gained here is a kind of polymorphism, the catch being that you need to know what the types are at compile time. So when you say, in my particular case, I've got one piece of code which implements all the controller base, and I have it in one application. And I've implemented a controller for that application which does something, and I have a completely different controller in another application, but it uses nearly all the same code. And I actually know at compile time that in this piece of code I'm always going to be using this one, and in that piece of code I'm always going to be using that one. And so at compile time, I can reuse the same piece of code and keep the same API, and in principle I could call either one as long as the object that I'm creating at compile time, it knows which type it is, and it gets routed through. And it's referred to as the curiously recurring template pattern, because you can create these polymorphic APIs without the cost of the dynamic lookup. And it isn't something you're going to be using every day, but you will see this out there. Is this something which I think you actually mentioned it on your initial slide, but did you mention it in a bad way or a good way?
At the beginning, we were telling that this was a good one. We avoided at the end because you lose the dynamic one. So there are other ways probably to do the same thing nowadays. Your screen is turning down, and so I would say it is an interesting thing. But nowadays probably there are other ways to achieve the same. Yeah, but it is an interesting pattern.
Anyway, as a thought experiment, if you understand what's happening in here, that when you call a pointer initialize and it casts it to the derived type and then routes that effectively, this function gets forwarded over to here and it calls this one, and there could be different ones, there could be multiple of these different ones. This is a very interesting, if you can follow the logic behind it, then you've gone a long way towards understanding how some of the sort of nasty template metaprogramming tricks get done. So going back to just how templates are set up, you can have default arguments. Here we've got a default T and U, or T and result. Result is char. Result, for naming convention, the result type of the function which we're doing here is a char, and foo returns a char, and we're casting that to a char. So we say foo of 65, it's going to print out the letter A, because ASCII character for A is 65, and A in 65 is a char compatible thing. If we specify that foo of int 65, this time, is it going to print out char, or is it going to print out 65? It's going to print out the char of A, because type name T is the first one, and the result is char, and we've only specified one int here. So we're saying T is 65, which is an int, and the second one is just going to default to being char. So explicitly int, result char. This one is deduced to be int, and result is char. And the third one, we're going to say int and int, and this time it will print out the number 65, because we're saying we're passing an int in, and we want you to cast it to an int and print it out. And so, or rather, we're printing out the result type here. We're not printing it out in the function, we're printing it out here. So it's int, it's 65. So you can have automatic types thrown in here, which the compiler will just insert if it can't deduce the other stuff. This is the exception to the rule previously, if it has to deduce everything, unless you supply a default, in which case it says, okay, I don't know what the result type is, but I'll put char in, as long as it works. And I mentioned as well, this 65.3, even though we said this is an int, the first type T is an int, and we've passed in, so the T is the parameter here, 65 T int, bad. 65 is not an int, but it's okay because we've used static cast result X here. We've explicitly cast our 65.3 into 65. Compiler says, I'm happy, it's okay. And this is where having, as you say, the explicit keyword on the conversion operator would say, that's allowed because you've statically cast it. If I didn't put the static cast there, in fact, it's a good question. If I take the static cast out there, I think it doesn't work, does it? it'll say 65.3 is not an int.
I think actually what happens is that when you say foo int, that's where the code is compiled, because now the template is completely defined. And then now you have a function that is called foo int, and you pass a double. And then when you pass the double to the integer, then it gets converted into an int. So it gets converted to an int when you pass the argument.
Yeah. And then it will fail, and it will say, I'm sorry.
No, I think it will work, actually. You can pass a double to an integer.
But 65.3 is a double, and it won't convert a double to an int. It'll definitely give you a warning, but I think it'll give you an error. And we could try this on...
Yeah,
what's happened?
I don't remember.
No, I don't want to power off. Why would you do that to me?
Because it's 5 p.m. He wants to go home.
It's 5 p.m.
Yeah,
well,
we can go on tomorrow morning.
That's perfect then, because then it's 5 p.m. So since we're still on default arguments, so unless they can be deduced, so we're on default arguments. You always put them on the right. So this is bad. Don't do this. Don't put result in the middle there. Put it at the end, because it doesn't make any real difference to the code, but it makes it so much more readable to the user. So if you put a result deduced in the middle, I mean, it still works. If you do blah, 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 all of this, and you say cout foo 65 3.5, it says, yeah, the result has to be a char because it was deduced, and we've got T is here, and A is here. And so A is here, and that matches that, and that matches that, and so this one must be a char. It's okay. It can deduce the two that aren't in the right order, and it puts the result in there. But just don't do it. Just put the result one at the end, so that, because it gets confusing when you see, so this one is int char float, everybody's happy. We've specified all three. In this one, in float, you can see by how long it takes me, because I even put this stuff on the slide, and I can't even remember which one's right and wrong, that it's basically, it's confusing. Because if you mess up, if you get these in the wrong order and you have a result type which isn't being deduced properly, well, it'll give you a compile error. It'll say, I can't deduce what the type is, and it'll say, so put them on the right, unless they can be deduced, but just put them on the right anyway. And we'll stop there, and tomorrow we'll continue with slide number 20. Remind me in the morning, slide number 20. Okay, I'll resume where we left off yesterday. I realized actually, there's somebody at the front here grumbled when I showed this slide, and I realized I'd missed off one little thing, which is, I said, for example, that if you change this compiles fine. You've got a structure, you've got an operator which puts it onto a stream and prints something useful out, and this compiles, and if you change this struct to a class, then it gives this error. The fix is just to add public to the class, and then this function can see the contents of there, and I realized that I didn't say that yesterday, and it kind of, I woke up in the middle of the night saying, oh, I should have said that. I didn't really, don't worry. So we left off talking about default arguments and how it's usually better to put them on the right, because then these kind of expansions down here are less confusing, because you can follow things from left to right and you can see where things are. And if you can deduce these ones, it's okay to put them in the middle, but it's just confusing, I think. So carrying on this whole business of deduction of how the compiler finds the version of the template that you're intending. When you have, for example, a parameter which is templated, which we saw an example earlier, in one of the slides where there was an x of an x of an x of an x, and there's a sort of recursive template pattern. If you have a function foo, for example, and it has here two template parameters, it has a t and a u, but the u is templated on something else, which we're going to call v. So how do you write that down in here? Now, in my head, I always kind of think, I want type name t, that's a complete thing, followed by a comma. And then type name u, that's a complete thing followed by a comma. And then you think, well, u is actually templated on something, so you put template type name in here. And I always want to put this v in here. But that actually doesn't compile. The compiler doesn't like that. What it's saying here is there's two template parameters. One is t, and one is u. Oh, and by the way, u is templated on something, and you just tag it on the end there. And you say there's a third template parameter. It doesn't actually matter where that third one is in the final construction. So the compiler will then say, okay, there's a t here and there's a u. Oh, and u is templated on v, which is okay, that's a parameter there. And so then when you try to instantiate something like, let's say this list of floats, it says, okay, float is the first thing here. That must be t. So t is a float. And standard, sorry, I'm pointing at the wrong thing. I've got a vector of doubles and a list of floats, and these are the functions. I was getting carried away. 4.5, 4.5, these are both doubles by default. I apologize, actually, the blue is a bit dark on this background, isn't it? Can you see the blues? Is that if I were to change the class template, would that become more visible? Yeah. If I do oops. Oh well, never mind. I will recompile the slides. No one wants to see how the sausage is made. And then I rerun that, hit the magic. Does it? Oh, it's not down now. I have to get the menu back and go. Oh, I can't see the menus. How do I get the menu back again? I need to go back into fit.
F5, or does that not work?
Say again?
F5.
F5.
Control Shift P for ocular.
Control Shift P. Oh wow, what was that? Presentation mode. Oh, I love it. Oh, you learn something new every day. Okay, let's see how. Oh, wow. Okay, the magic of having other people who know what they're doing. You'll learn this when you do templates. You know, get someone else to do them if you can. We're on to about there. Oh, that's much better, isn't it? Gosh, so bright, I need glasses on. Okay, so we've got two functions, foo. 4.5 is a double. So we expect t to be a double in both of these instantiations. Sorry, here's the template, here's a specialization, and here's two things which we're going to put into here. Now, the vector t and the vector l, I don't know why I've called that t. I meant to call that vector v because it's a vector, and that one l because it's a list, but don't worry about the t. Imagine that's a v. So these two functions are going to call specializations here. Now, the first one calls the second, and the second one calls the first. Now, why is that? Now, the first one calls the second. This is a double, and that's a vector. And double, vector, it matches the first specialization. This one here, vector, matches here, it's fine. But t here, double, fine. U of t, that's interesting. This is a vector of doubles, and this is a double. So t of x and u of t, double, vector of double, is a better match than the first one up here. So this vector picks the second specialization. And this stuff coming out here, when you do type ID of a type and print out the name, for double it just prints D. For standard vector of doubles, it prints out this nonsense here, which it's very hard to read. And this is actually, when Fawzi showed the intro slides and he was talking about ABI compatibility and whatnot, the way that the compiler represents these, I mean, a double is a double, it's pretty straightforward, but a vector of doubles is something much more complicated. And the way the compiler represents it internally is much more complicated. So these things tend to be a little bit gobbledygooky. Like this one here, when we print out the list, I mean, this is nonsense. And when you have a vector of lists with a map of this, that, and the other, and you bung that, all these things become quite complicated and long. So I've got a little utility, which I'll show later. So vector of double matches this second one. List of float, well, t in this case is a float. I beg your pardon, t in this case is still a double, but u of t, that's a list of float. It doesn't match this template, so it picks the first one. So when you're specifying templated parameters with templates of templates, then the same rules basically apply as with the simple ones. And you might think, well, how would I do a template of a template of a template, like a three-order deep template? How would I fit that? Because here we got T, and here we got U, and then you tag a V on here. Would we put a template type name inside this curly bracket and then put a W at the end here? And the answer to that is, well, it doesn't really work, and actually you don't have to, because when you saw this example back here, oh, I'm going the wrong way. When you saw this example here, and I said, for example, that, so this, for example, x of char, x of int, all of this matches a single, just remind myself, let's pick the first one because it's a bit easier. But so the whole of this thing here, or in fact, this one is a template of a template of a template. So this second one, B, all of this X matches one of these sort of U's. Even the fact that X is templated on something, which is templated on something, and on something, you can kind of ignore all that and just say it's still a single object. So when you come to do templates of templates of templates, you don't kind of have to worry about it because you can create a templated thing which just works like this. And then normally what you have is something like a struct. And inside that struct, you can have a secondary struct. And then you can template that on more template parameters. And so you can then take this U, for example, may be templated on a V, which is templated on a W, and you can kind of recursively do it inside the struct that you're building. So you don't ever have to worry about having a third or a fourth order template because you can basically write everything in terms of just two templates and then specialize inside the template on the thing. And that makes life actually a lot clearer and easier. It can get quite complicated, some of these nested things. It's interesting that you don't have to have types like vector and list and double and float. You can actually template something on a number, like an int, for example. You can say, I'm going to create a structure which is templated on a number like 3 or 7, 12, as long as that number is something which the compiler knows up front at compile time. And so you can say something like a static int. I'm going to say, it's templated on an integer, and when I create static int 5, the value of that will actually be printed out as 5, and the static int of 6, the value of that will be printed out as 6. And this means that, for example, you can template, for example, I mean, do I mention it on this slide, or maybe I mention it on the next slide? Yeah, this sort of thing is really quite useful for if, for example, you've got a message buffer or you've got some little padding space somewhere. You may see it in a minute when later on today or tomorrow when people talk about cache line padding, for example. You know that a cache line is 64 bytes. And you've got a thing which you know is going to be like 27 bytes or maybe 54 bytes or something. And what you'd quite like to do is pad it out to be the size of 64. So you can add in an extra pad and you can template that on a size of something. And you can say, make the space that pads this out to be exactly 16 bytes or 13 bytes or whatever it does to take you to a boundary. And you can put these objects which are templated on an integer, and you can actually template not just on an int. This here, in this case, I've said templated it on an int. You can template it on other things as well. Anything which the compiler knows up front. And you can specify a default size, for example. So if you know, you'll see things like sometimes a string. Strings tend to be allocated on demand. You say, I'm going to say hello world, and it says, oh, I need 10 characters to store that. So it allocates 10, puts hello world in it, and it moves on. And then you have a longer string, and it has to deallocate the 10 and allocate 50 and put that in. Things like small buffer optimization, they'll say, I'm going to allocate some space up front, which is going to be, let's say, 16 bytes or 32 bytes. And then if the string is longer than that, I'll allocate some memory. But if it's less than that, I'll just use that. And you can say, for example, here's a container. This container here is default double and default size 10. But you can say, here's a container which is double and size of, oh, I haven't specified size, I beg your pardon. I should have put a value of size in here. Oh, this is wrong, actually. I beg your pardon. This size should have been a fixed number, not just the variable size, which I've left in there. That's assuming this is a const. I should have put a const size equals, let's say, 32 or something. So this one doesn't compile because I've said 100, but that's the second parameter. And the first one, how do you deduce what t is from here? The compiler doesn't know. It could be a float, could be a double, could be an int, could be anything, could be some user type. This one doesn't work. But you can put default parameters for non-type parameters as well. And this actually turns out to be quite useful in general. Another thing you need to watch out for is if you have a complicated expression like this here. So you have a struct, and within that struct you define a new type. And in this case, we're just defining the new type to be B. And I'll come again to these alias types, and I think it's probably the next slide that we're coming to. So in this case, this type here is just B. And so if I say, if U is defined, so this is a template. Order is a template which takes a T, a U, and an X. So it's got 3 template parameters. T is supplied by whatever is deduced from gosh, I don't like it when you put a slide up and you forget what, forget what you were going to say here. So in this case, order is templated on B. So template type T is B, which is a struct. And U is T type. Now, B of type is B. So T is B, and U is B, and X is whatever U value is, which in this case is a number 100. So order of B is B, B, 100, and we're all happy. And in this case, B2 is B2 here. T is B2. U is whatever T of type, which is the value of B2 type, which in this case we've defined to be a sub-object inside here, which is C. So U is B2C, and X is the U of value, and U is the B2C, and it has a value of 42. So that's fine. This is a B2, B2C, and the value 42. And the compiler can follow that. It's nasty, but you can follow it. Now, if you change these round, and you say T, U, and X swapped. So in the previous slide, just to remind you, I've done it again, I pressed the wrong key, sorry. If I go back up to this one, here I've got U, X. U is defined before X uses U. If you do this and you say X is U and then U is this, the compiler will now throw you an error and it won't compile that. It will say, I'm sorry, U hasn't been declared here because U comes after that. So it's something to watch for. You'll see error messages when you do some of these constructions, and you'll get errors and you'll think, I don't understand, but you can follow. The compiler can't follow that. And it's just one of those things you have to watch out for and be aware of. Template 2 is not valid. So I talked about saying using. This keyword using, if you've used C, C++ in the old days, you'll know that there's something called a type def, where you define a new type based on an old type. And type def int, integer type, says integer type is basically defined as being an int. And this is not particularly useful because you usually want the things that you define to be shorter than the things you're replacing, not longer. But you can say using integer is int, and that's fine. The compiler says from now on, whenever I see the word integer type, I'll assume it's just an int, and that's great. Everybody's happy. What's different about the using keyword from the old type def is that you can add templates to them. So you can say, well, my type is templated on T, and from now on, whenever you see my type of T, replace it with standard vector of T. And so now my type of double is actually a standard vector of double, and there's a constructor which is called standard vector of double with 100. And that's fine. The compiler says that's great, and it's happy with that. Now, this doesn't save you much money in the sense that, I mean, changing vector for my type hasn't really bought you anything. All you've done is change one word for another. But things get more interesting when you have something more like this, for example. So this is a template structure. So my container is templated. It's templated on follow the commas. So inside this bracket, we get to this comma. It's templated on T, and it's templated on U, and there's also a default allocator supplied here. When you look at that, you just recoil in horror because it's very hard to see what the hell's going on here. So you're saying my container is templated on 2 things, and it's given an allocator. And what you normally would write is standard vector of int, standard allocator of int, and there's a v where you've instantiated one. If you say this, the user can now just say standard vector int, and so you've removed one level of abstraction. You've removed one degree of freedom, if you like, from what the user has to write, because you've supplied this standard allocator int is now just an int. What you've done in here is you've basically said my container, which in this case T, the first parameter, is a vector. So you're saying this is a vector. U is whatever the vector is templated on, which in this case is going to be an int. So a vector of int, the U would be an int if that was expanded. In this case, standard vector int, standard vector, type name U, is actually taken from the second parameter, I beg your pardon. What's happening is we're substituting backwards in the other way rather than deducing. You're putting standard vector into here. Standard vector is templated over some things. Int goes into the U parameter here, and then allocator of U gets inserted in here. So instead of writing that, the user can write that. So you've saved a little bit of work. Now, when you have more complicated structures, each time you reduce the complexity on the user, you make things a little bit more accessible. And you'll find that when you look through things like, for example, standard library code, or some of the code that the people here are writing. So our job is to write these libraries with things like grid tools, things like the Pico, the HPX libraries, which do all sorts of complicated things, and they're written in generic terms. If you look at the source code in those, you'll see huge, great, long template expressions like this, which the user in the end can just do something simple like that in, which is much, much cleaner. And your job, if you're writing these libraries, is to be able to present the user with a much cleaner, simpler sort of end thing that they have to type. Be aware that when you say, my vector is a vector of t and my allocator of t, and I didn't mention that the standard library, for example, all the vectors and the queues and the lists and everything, they by default, they also have allocators which are given with them. We kind of assume you all know this already, but maybe you don't. But for example, when you allocate memory for a vector, you can tell the compiler where to get it from by providing an allocator, and that's a template parameter, which is usually defaulted, but sometimes you want to customize it. So you provide an alias like this, and then you maybe specialize something based on this alias. And then in another piece of code somewhere, you do a specialization and you forget that you've got an alias of this one to this one. An alias is like a symlink in your file system. It doesn't create something physically kind of new. It points to something else. So if you try and create a specialization for a function doing that, and a specialization where my vector t, my allocator, is actually exactly the same as the using here, you get effectively a collision. It says, the compiler will say, you've defined the same overload twice. Don't do it. So watch out for that kind of thing. Same thing here. In this case, we've actually reduced. So this vector int, allocator of int, we specialize on vector of int, allocator of int. Oh, I've got the screen here. I can look at it much more easily here. This follows on from the previous slide. This 3 and 4 corresponds to the 1 and 2 on the one above there. So we've defined some overloads here where we compute the size of the vector by returning v of size here. If we then simplify our template by reducing the number of template parameters the user has to supply, so that we've effectively reduced it down to just a single instance here, we get the same problem, that even though we've changed what the alias, what the template instantiation, the alias looks like, we've reduced the number of parameters down from 2 down to just 1, then if you say my vector of int, you're effectively still overloading the same function as before. By changing the shape of the templates, by using the aliases, you haven't actually fundamentally changed the thing which you're passing into here. This is still the same thing, and so this says you can't do it. More on deduction of arguments and which specialization the compiler chooses. A container templated on t and size here, you specialize it. Normally inside these brackets you put some code. This is just here to show you how it works. So normally you would say, I'm going to put some code in here which does something special, and typically this is for things like the small buffer optimizations, these kind of things. if you have a container which is templated on char and 10, which of these overloads is it going to use? By default, we're assuming a double and size 10. Here, we've got a specialization for anything and size 10. Here, we've got a specialization for anything and size 15. So anything in size 10, we would expect it to use this specialization number 1, because this is a better match than the default. So if you specifically say 10 here, rather than just letting the default be 10, then this is a better match. Specialization 1 is a better match. In this case, float, 30, T10, T15, nothing interesting there. It goes for the default one. Int 15 chooses this one, specialization 2, because this one is a better fit than the defaults. And then if you just say int, so T is int, and you haven't specified the size, it's going to use, it's interesting here, because you might think that this one is going to use the default, primary, because you've specified int and you've left the default as size 10. But because the default is size 10 and you've actually specialized for size 10, this version here will actually call this specialization 1. It's a kind of little gotcha. You need to be careful, because sometimes you'll write template specializations and you'll run your code and something weird will happen and you won't realize that the wrong specialization is being picked. And you need to be aware of the way the lookups are done. And likewise down here, if you just say nothing and nothing, in this case, nothing, this 10 matches this 10, so this is picked for the fourth one here. But this nothing and this nothing, T is not a better specialization than anything here, so this one actually picks the primary. And I find these ones these last two here are a little bit confusing, because you kind of wonder how the compiler is going to decide which one of these it's going to choose. And so you need to sort of remember these little corner cases. This one I find very confusing. When you look at this one here, you've got a structure X, and in the constructor of that, I've just printed some stuff out, and you've got another structure, and you've specialized it, and I've printed out this here. So when you run this code, you'll either see primary or specialization printed out. Now, without looking at the output at the bottom, if you say, if I create an X templated on A, and struct A just has a using value type equals int, what is X of A going to run? Well, X of A, I've said, I'm specializing on T with the default second parameter of int. And I've supplied A. So T is going to be A, and the second parameter is going to be int, because I haven't specified anything, and it says U is equal to int, and the specialization says that U is going to be equal to T extra type. Okay, what's T extra type? Struct A, well, it doesn't have an extra type. So it's going to say, okay, T and U is int, so X of A just uses T int, it uses the primary specialization. So the first one prints out primary 1A. The 1 refers to, that's just the type of A. It's just the compiler deciding to call it 1A. It should just be A, but don't worry about it. So B, you've now specified this extra type as an int. So T is now a B. B has got an extra type, which is an int. Aha, okay. I've got a B and I've got an int, so that matches this nicely. And I've got a B and a T, which is an extra type, which we know is an int. And so this is a better match than that one. So X of B prints out this one, specialization. So the second one prints out specialization B. That seems fairly reasonable. C, we've specified extra type as float. Now, template T is a C, and template U by default would be an int, but here we say T extra type, T extra type is float. So how is it going to decide to use this specialization or this specialization? And the answer is that when you do this construction here, you've reduced the number of template parameters down from 2 to 1. we've reduced the parameters from 2 to 1. We only use this specialization if this T extra type matches the U. So if this T extra type matches the U, then it will go for this one. But if this T extra type, which in the case of C is a float, it doesn't match that, so it uses the primary. Now, I find this somehow contrary to my expectation. I expect C, because you feel like you've done more specialization in here by saying specifically use T extra type, but it just doesn't quite work that way. And this is another case where you'll write some complicated... It doesn't so much happen when you write a single example. You write a simple example and you get it working and you're happy. The problem is when you then pass this as a parameter to some other function and there's more of these things embedded in other things, and the compiler is now kind of doing recursive lookups of this, that, and the other, and you get these corner cases where things don't quite match out. And so it's important to note these things. In the case of struct D, the extra type is a char, but it's interesting. Oh, sorry, I've skipped one. We've gone from C. I've skipped B. If you say B and you specify the second parameter U is a char, this is interesting because B, extra type is an int, and now we're saying B is a char, and we say B. Now, in this one, it used the specialization. When we said x of B, B's extra type was an int, and that matched the first, that matched this one. So the first one here matched the specialization. The second one where we say B, but using a char, it no longer matches it, so it falls back to the primary template. And likewise with this final one here, if we say D of char, D has got an extra type which is char, so this extra type char matches this U type, so it will use the specialization. And it's this business of looking up stuff and cross-checking, it's quite confusing. I don't like this slide at all. So we'll move on. Now, has anybody heard the expression sphinae? I don't know how it's pronounced. I call it sphinae. Does everybody else call it sphinae? And it stands for substitution failure is not an error. And what the hell does that mean? What does it mean substitution failure is not an error? Well, what it means is that when you create templates, and then you provide specializations for those templates, sometimes you're going to say, template it on this, and instantiate this using that, and some of the specializations won't compile. Some of them will, and some of them won't. And what this substitution failure is not an error means that just because one of the specializations doesn't compile, it's not an error. That's allowed to happen. And it's kind of the backbone of how the compiler does its stuff. If everything for every possible combination of every substitution of every template in everything had to compile, you would be really in big trouble. To give you an example. You've got an X, and it's templated on T and U, and by default U is an int. And now you say, I'm going to specialize X on a T, and instead of U being an int, I'm going to say U is whatever extra type is, which is actually basically what we saw on the previous slide here. We said there's a T extra type. Now, A here, if you put A into this template specialization here, and you say struct A, so T is A, and this U parameter is now U of extra, is A of extra type. Well, A doesn't have an extra type. So by all standards, that shouldn't compile. That should be an error. But sphinae says basically substitution failure is not an error. So if this one doesn't compile because T extra type doesn't exist, that's okay. You can just choose this one because this one does compile, and so that one matches, and this one doesn't. And so what this is basically saying is you can have specializations for tons and tons and tons of stuff, and they don't all have to be valid. But the best valid one that works is the one the compiler will pick, and the ones which don't work won't cause your code to basically stop compiling and stop working. So when a substitution fails, the compiler just ignores it and moves on. It says, okay, it's allowed to fail, it's not an error. When it succeeds, it says, okay, that one succeeds, that might be the candidate I'm looking for. And it goes through all of them. And then when it finds the one with the most number of sort of specialization matches, it picks that one. And hopefully today or tomorrow, you'll see some slides on concepts and also const if. Concepts and const expressions make a lot of this disappear because instead of having stuff like this, you can use concepts. So What's Spinne useful for? Spinne is useful for this. You can say, I've got a struct A, it's templated on T, and I'm going to put a default parameter enable, which is void. And void is a valid template parameter which says you can just drop it completely. It doesn't have to be there. So you can just have a single parameter, and if enable is not present, it doesn't matter. And now I'm going to say, I'm going to specialize this, and I'm going to say A is templated on a type name T, and whatever the result of this is. And so you can say enable if the type of T is the same as an int, then whatever the value of that is, so there's a structure called isSame, and it's got a value inside it, which is going to be either yes or no, true or false. And if that's true, then enable if is going to put a void in here, and that enable void effectively becomes nothing. The type of void is just nothing, and that just becomes struct of A, and it says yes, that's okay. And in this case, you can say, if it's not the same, then this will return, instead of true, that gets flipped to a false because of the not there, and this becomes a void type, and it'll print not an int. So if you say A of int, it prints out, it's the wrong way around. I beg your pardon, I've got these the wrong way around. A of int prints out int, and A of float prints out not int. Oh, sorry, that's not a not sign. I've confused myself. That's an exclamation mark, not a not. That's correct. It says int, and it says not an int. And what's happening here is the first one matches this specialization. And if you look at the definition of enable if, in fact, really, the definition of enable if is in 2 slides' time. So, it's 1 slide. So if you look at the definition of enable if is defined as just a structure. These are, you can implement it in multiple different ways, but enable if is just a thing which says, I'm templated on a type B and a void parameter here. And if you specialize it for true, then say type is T. And if you don't specialize it for true, then there's no type T. The default has no type in it here. There's no type T. So if you go back to that slide and you say enable if is the same as T, and just assume that is the same works, and it either returns true or false. If this is false, then this slide has got nothing. So this thing here is actually a false, what's the word I'm trying to say? It isn't empty, it's actually a compilation failure, because there's no type in this. So, because there's no type, there's no type. There is a type for true, but there's no type for false. So if this is false, this type basically doesn't exist, and that's a compilation error, so it has to pick the other one. And when you put the not sign in there, you flip them round. And it's equally valid to either say enable if is an empty construction and you specialize it with a type. You can actually not even define anything. You can just leave enable if completely unspecified in the case of false and define it in true. This is not this is because you've actually put a curly brace here. You've actually created a class effectively based on that. In this one, you've just created a declaration that there is an enable if kind of exists, but we haven't actually created the class yet, and then we're only creating the class for enable if true. And the Spinne is basically saying, yes, if this compiles, it's allowed, and if it doesn't compile, we're allowed to just skip it. And it's the way that a lot of the template metaprogramming that's done in all of these libraries is handled under the hood. And hopefully some of this Spinne simplifies with concepts. Here's enable if type and standard same. Instead of writing enable if is the same value, and then all of that, the type of the is same value, you can use enable if t, and that gives you enable if is the same. You've effectively got away with the value and the type here because there's some utility features which are called is_same underscore type and is_same underscore value. This gives you the value of that, and this gives you the type of that. So you've skipped off the colon value and the colon type from here. And this is exactly the same as the previous one, but it's a lot easier to read. So use these rather than the other ones if you end up, and cruft is an English word, which means stuff that's just baggage that gets handled around. And there's lots of little utilities around that make your life simpler. Okay, how are we doing time-wise? It's 9:00. I've used my half an hour, haven't I? So I better get a move on. Classes, templates. To cut a long story short, when you create a class and it's templated, and then you use that class, you have to tell the compiler what the template parameter that goes into it is. And class template type deduction, also referred to as class template argument deduction, is how the compiler decides which version of structs to use. And in old C++, you had to specify that this was an A of an int and then pass x of 3 to the constructor. In the newer C++, you can say y of 3, y, which is a struct A, and just give it a 3, and it will just guess the type T because the constructor takes a T and it effectively refers back to there. And this is really, really handy because when you have things like a function here, which I'm going to declare as a little lambda, which you're going to be told about later on. A lambda is like a function you declare on the fly. I won't bother you explaining the syntax, but there's a function, and the type of that function is horrific. I mean, nobody wants to know what the type of a function is. It's like a pointer to a thing which takes a bunch of arguments. So we use an auto keyword. And you may have a class which takes a function as a parameter, a template parameter. Imagine if you write a sort algorithm, and the sort algorithm is beautiful. It sorts things. It says if this one is less than that, then swap these two around, and if this one is less than that, then swap these two around and move this one from here to here. And if your classes, your things you're sorting, have got operators less than, and they've got move operators, and they've got maybe some sort of overload of the swap function, then you can write a sorting algorithm which will sort all these things, and you can give it ints and vectors and doubles, and you can give it your matrices, and it will sort them into whatever order because you can specify the rules. And if you allow someone to sort things from smallest to biggest using, say, the less than operator, if you write your algorithm genetically, you can actually allow them to sort them from biggest to smallest by, instead of supplying the less than operator, by supplying the greater than operator. So you can pass functions in. And that's when generic programming starts becoming really quite kind of interesting, because instead of having an algorithm which is fixed, you can allow people to customize it by not just passing in the type, but passing in the functions. And so when you have stuff like this, and then the user has to know the type of everything before they call it, it's awful. And so this class template deduction allows the user to create a thing, and the compiler just works out. I mean, if you had to know the type of this and the type of all the things, and then what's the type of this B here? Well, you can use this. There's a nice keyword, decal type, which just says, give me the type of this, and create an instance of it and move this into there. You can drop this with this deduction. You can just say, give me a B and take these parameters, and the compiler will just work it out. And it doesn't actually matter what the types are on this slide. Since I'm running a bit behind time, I will go quickly through this. Things like you saw yesterday morning, shared pointer, unique pointer, that kind of, I keep doing that, sorry, the power button's next to the page down button. Instead of saying shared pointer of array of ints, you can just say shared pointer and pass it an array of ints. And the compiler says, well, this is an int, and it's int of 10, so it's an array of ints, so I know it's a shared pointer of int, and it will instantiate the correct version of the shared pointer with the correct destructions code that will delete this at the end. It does everything for you, and makes your life much easier, much simpler. The compiler's doing the heavy lifting. It's actually internally, the way it does all this is basically the same as function lookup. You know, it can create a temporary function which makes an object and a temporary function which makes an object, and it can instantiate them. I won't go into that. You can look at these slides if you want later. The auto keyword, we've seen it on a couple of slides. The auto keyword is the compiler knows what things are. Even if you've made a mistake, which frequently you do, you write stuff, and then I want the result of that and that. And the result of an int plus an int is usually an int. But the result of a matrix plus a matrix, it might be another matrix, or it might be something, you might have overloaded the operator, and you might not know what the result type of something is. So you can save yourself a lot of pain by using the auto keyword. You can say, here's a thing 1 and here's a thing 2, and I've overloaded the operator so that thing 1 plus thing 2 returns a thing 2, but thing 2 plus thing 1 returns a thing 1. Which is a bit confusing. It's like having int plus float returns an int, but float plus int returns a float. And you know, it's like int divided by int Should you return an int from that, or should you return a floating point from that? 6 divided by 4, it's 1.5. Does the user expect 1, or does the user expect 1.5 as a result? The types sometimes of these custom operators aren't. The auto keyword will just make it all go away. You can just put auto in. And same as those other examples we've seen where things get more and more complicated. So variadic templates are wonderful because instead of supplying a list of parameters, you can say, instead of specifying all the parameters, you can say, here's a list. And you can say, here's a function, it takes some arguments. I don't know what those arguments are yet, but if those arguments match a particular pattern, you can specialize on patterns. So when you call function with arguments, it basically expands your pack to arg1, arg2, arg3. The way you define an argument pack is you say template, type name, ... and then this TS, you can call it anything you like. And then my function takes these arguments in here. This is the definition of the parameter pack, and this is the actual, the actual contents of the parameter pack, if you like. And you can actually, the nice thing about parameter packs is they can be completely empty. And when you expand those parameter packs, you get arg1, arg2, arg3. If you put, say, function brackets args ... bracket, it expands to arg1, arg2, arg3 inside the function call. So that would be function arg1, arg2, arg3. If you have some pattern followed by args ... that actually, because the ... is outside this bracket, you actually get pattern arg1, pattern arg2, pattern arg3, pattern arg4, and this one, if, for example, you take the reference to a function, you get function reference R1, function reference R2, function reference, and I apologize for forgetting to put function in here, in this one. This is really, really useful, and it's used all over the place. You can ignore this. Basically, whatever the dots follow is the thing that's expanded. And sometimes people put the dots in front of the next thing. It can be confusing. How's this useful? Well, let's make a simple function which prints some stuff out. I want to do a pretty print of 3, hello, 42, and world. This is a double, this is a string, this is an int, this is another string. But I want a single function which prints them all. Well, the nice thing is because the standard template library has provided a stream operator for standard cout, which takes this little stream operator, if I do pretty print of, here's a basic function which takes basically no parameters. And here's a specialization of that, or rather, here's a templated version of the pretty print function, which takes a stream, and it takes a first, and it takes a list of values. Now, this is interesting because if I call this function with 4 parameters, and I strip off the first one, and then I call the function recursively with the remaining 3, now t gets put in here, and these values go in here, and then the first one of these values becomes the new first of this one, and then so you call the function with 4, and then you call it with 3, and then you call it with 2, and then you call it with 1, and then you call it with none, and then it prints out this none version here, and so it prints out this. And so variadics allow you to do these kind of recursive expansions, and much, much, much more. And I should mention perfect forwarding because it's used a lot in all of the sort of metaprogramming and generic programming. You have a function which is templated on a bunch of arguments. When you put this double ampersand here, this is a very special. You saw yesterday how the double ampersand means move. When you see a template parameter with a double ampersand, what that means is that if you pass an int and then you forward it, it gets forwarded as an int. If you pass in a reference to an int, it gets forwarded as a reference to an int. If you pass in a const reference to an int, it gets forwarded as a const reference to an int. Whatever the type of the object that's passed in here, it will get forwarded as the same type. There's lots of places where you'll put some code in and you'll take a parameter and then you'll pass a parameter through and you'll lose a reference or you'll lose a const or you'll lose some modifier which is passed on to I mean, an int is different from a constant, and an int is different from a reference to an int. And you have to be careful about that. And this perfect forwarding, you'll see this everywhere in templated code, and you need to kind of understand it. I think we'll skip fold expressions. When you expand a pack, there's some ways you can do some clever stuff using fold expressions. Basically, in the code examples, if you check out the code, you'll see in each of the sessions that we've done, we've got the slides, and there's also a little code folder. Have a look in the code folder, and you'll see some things that pretty print that we did using a recursion. You can actually do it using a fold expression, which expands a pack out and does it in the same kind of way. Constexp is anything that the compiler knows is a constant up front can be flagged as a const expression. So the number 5 is constant, and the compiler knows that the number 5 is a constant. And you can have a function which takes an integer, and if the integer is known to be a constant, you can tell the compiler effectively could you just calculate that value right now? So if you said 2 times pi, and pi is defined as a constant, and 2 is a constant, then the compiler knows what 2 times pi is, so it can just put 6 point whatever in for you. You can put constexp in front of certain constructions. They can be in front of variables, they can be in front of functions, and it allows you to write stuff which the compiler can evaluate at compile time instead of runtime, which of course is very, very handy if you want to, I'm trying to think of an example off the top of my head. Is there anything on the slide that tells me? In this particular example, for example, this is a constant string, and it has a constructor, and the constructor is marked as constexp. Now, it's interesting that if you put constexp in front of a function or something, the compiler will try to evaluate it at compile time. It'll say, it's const expression. Maybe I know all the parameters, and so I can do the result beforehand. It doesn't have to be const. You can still use these functions with non-constant things, and you can still pass variables into them, and then the compiler will say, I don't know, and I'll leave that till normal runtime. But if you, for example, create if I create, this is probably a bit too complicated since we don't have much time, and I should probably just skip over it. But you can create a string, for example, which is known at compile time by having a constant constructor, effectively a constant operator, so that you can get characters out of it. What we're doing here is we're counting the number of lowercase letters in this string. Now, because we've passed hello world into the compiler, it's not a variable. It's not something which the user typed in at runtime. It's actually, the compiler knows this string hello world. So if we say count the number of lowercase characters in hello world, it can find the function count lower. It says, I can take one of these. Perhaps constra was not a good choice of name because it's confused, but this is just a class called constant string. And we've got a constant string as a parameter, and it's going to go through here and count all of the characters which are lowercase or uppercase, and it's going to do all of this at compile time, so that if you, I didn't put a link in here, if you compile this, the actual code generated effectively drops down to basically nothing. It just puts the number of characters in there. The compiler does it all for you at compile time. If you were to do a Fibonacci, so that, for example, that pretty print that we did, where we printed the number of strings as 4, and then we passed the 4 to the 3, and then we passed the 3 to the 2, and we passed the 3 to the 1, and then we hit the 0, and then it came out. You can do the same thing with a constant expression at compile. So if you wanted to know the Fibonacci value of, let's say, 6, you can say, if at compile time you say Fibonacci of 6, then this will all get evaluated directly by the compiler, because all of these are declared as constant, and this is just a constant number, this is a constant number. Fibonacci of n minus 1 is actually a known number if n is known, and Fibonacci of n number 1 is known. And instead of the templates being recursively created, this will just evaluate this directly in the compiler and give you the answer. I've got a couple of slides on metaprogramming, and probably, due to time, I should keep it thin. The secret with metaprogramming is that with normal programming, you're working with kind of data and you're computing things. Metaprogramming is you're manipulating types. And things like enable if. Enable if this is the same as that returns either a true type or a false type. And based on the value of the true type or the false type, you can instantiate this function or that function. You may say, I've got something I want to calculate, and I've written my calculation function with a specialization for the CPU and a specialization for the GPU. And if, for example, the type that I pass into you is a GPU tag rather than a CPU tag, then instantiate this and instantiate that. And you may get the types. How do you know if you're running on the CPU, or how do you know if you're running on the GPU? You may have some other helper functions which are doing this sort of thing. And you can manipulate types based on the same kind of things we've been doing here. The classic example for me is in things like loop fusion and kernel fusion, where you say, I've got a stencil operation, and the stencil operation takes this, and let's suppose you say, I'm going to add these two numbers together, and I'm going to return a result. And then I'm going to pass the result of that into another function, which is going to add something else and add that to that. And with metaprogramming, you can say the type. If you add two numbers together, let's suppose the example, you add two ints together and you get another int. Or better still, you add two matrices together and you get another matrix. If you write a template function which says, when I'm given a matrix and another matrix, instead of returning the answer of a matrix, I'm going to tell the user that the result type isn't matrix, but the result type is the sum of two matrices. Now this is interesting, because if you take the sum of two matrices and you pass it to a multiplication function, or in fact it's probably better to do it the other way around. If you take two matrices and you multiply them together, and then you pass that to a sum function, if you evaluate the matrix multiply, actually no, the first example was better, I'm confusing myself. You take two matrices and you add them together, and you pass them to some other function. You do the calculation of the matrix addition, and then you pass it to another function. And you can create a specialization of a second function, which says, if I'm given the type, which is the sum of two matrices, then do this. If I'm given a matrix, do this. But if I'm given the sum of two matrices, then do this. I chose the example the wrong way around. Hannes at the back, he knows because he does this all the time. If you have... It's too confusing. You should write it all down. Does anybody have any clue what I'm trying to say? Is instead of returning a result, you return the result, but the result has a certain type. And you can specialize a function so that if A plus B, if A is the result of a matrix multiply and B is the result of a matrix multiply, then do something different from if A and B are just matrices. And what this allows you to do is effectively, you were going to ask a question.
Yeah. I'm trying to follow you, but are you aiming towards the size of the matrix can be different depending on the result of the previous calculation? Your dimension of your matrix changes. So if you have one matrix plus another one, it will be the same, in dimension. But if you multiply, the dimensions change. Is that what you're aiming at?
I should have thought of a more clear example before I started speaking. What I really wanted to say is it's not so much the size of the result that's the important thing. If you have something, for example, like A plus B times by C, now you could compute that as A times C plus B times C. So now you've done A times C, one multiply, B times C, another multiply, and then an addition at the end. Or you could do A plus B and then multiply by C, and you've done one addition and one multiply. So if you have a function somewhere which returns A times C and B times C is returned from somewhere else, you've got two multiplies and then you add the results. You've got two multiplies and an add. If your function just evaluates that and does it, you get the answer. But if you know that the type of A times C isn't a matrix, but it's an A times C. It's a matrix times a matrix. And I know that the type of B times C is a matrix times a matrix. And then I've got an addition operator. And I specialize the addition operator so that if I know that one of my left operator and my right operator are the result of a multiply operation, if they're both multiplies and I'm a commutative operator, then instead of letting the compiler like multiply, and then adding the result, I can specialize my code in such a way that the parameters from there get passed into me and I reorder them and I say A plus B times C instead of A times C and B times C and then adding them. And to do that, you need to know the types of the results of operations and not the values of the results of those operations. And so metaprogramming, where it gets interesting is where you can take something and reorder it and produce something which is better than what you started. Obviously, you don't want to reorder it and produce something worse, but if you can reorder it in some way and produce something better, and metaprogramming is all about doing that kind of thing, and it lets. So Hannes and people at the back are working on the grid tools library, which is used by the Meteor Swiss, and it takes stencil operators where you're doing, you've got the pressure, the temperature, the velocity, you've got the atmospheric conditions going on, and you're doing all these stencil operations, and you're frequently doing one stencil operation, another stencil operation, another stencil operation to compute all these parameters, and you're iterating over all the numbers, and then iterating over all the numbers, and then iterating all the numbers. And if you know that these iterating patterns could actually all be done at the same time, you can fuse all of those iterations into a single loop instead of multiple loops. And so you can say, hey, compute this, and then store all those results in one place. This is where metaprogramming takes you. And you need to know the types. You need to be able to, to automatically throw away const type things and have them inserted directly by the compiler. You need to be able to you need to be able to allow the compiler to simplify what the user has effectively written. And this is why DSLs, remind me, what does DSL stand for? Domain-specific, thank you. Domain-specific languages come into their own because you can force the user to write their sort of equations and whatnot in a way which you have specialized all of the things so that the compiler can do this stuff. And it's useful for us when we're creating these sort of libraries which do heavy work for other people. I'm going to skip through. So this factorial, we've just seen an example of basically the same of. Am I right in thinking that you guys are going to talk about template metaprogramming a little bit more later? You're going to mention it, Hannes. So it took me a while to get there, but I think I tried to convey to you what the purpose of the metaprogramming is all about. You tend to find there are some conventions. So it kind of template metaprogramming, it wasn't something that was intended when C++ was created. It was something that everybody said, oh, you could do this. You can have a template of this, and you can manipulate the type of this by returning, a struct can have a type inside it, and it can have different things like result types and param types. And based on those types, that you can have constructions which take the type from other objects. And if the type of that other object is this type, then do this. But if the type is that, then do that. And then that produces more types, which you can then have more. And you can do this logic. You can make the compiler work through this logic rather than having actual if statements in code which do things dynamically. And conventions are that you tend to have things like type and value. Almost every type has within it another type and a value for something, and these are the conventions that get. I'm going to skip this. Okay, actually, no, I'll keep this in because it's kind of interesting. Integral constant. It appears in the standard library, but what does it do? The value of t. Integral constant based on an integer of 7, the value is just 7, yeah? We expect the value of 7 to be 7, that's fine. But what we've done is instead of using the number 7, we've created a type which represents the number 7. Now that's kind of interesting because now the number 7 is different from the number 6 and then it's different from the number 5 and things. And so there's a function in the standard library called standard rank. Now, in the old C-style program, you might have an array of values. Let's say a matrix would be 3 by 4. And that's the same as an array of 3 with 4 things on it. And so you can create a template where you say, what's the rank of an array? And I'm going to inherit. Integral constant is a struct. It's interesting because it doesn't actually have anything in it. It's kind of empty. When you create one of these, it doesn't cost you anything because, I mean, there's nothing in here. I'm going to inherit from the integral constant based on a size and a default value of 0. So rank, without any specializations, just gives you 0 because the parameter that comes into here, the second parameter t, the value is just 0.